Okay, so now have a think about what we have learned yesterday. Before page 2, we do everything is like, I know exactly what the population is. Okay, I know the exact proportion. What is that? I know like everything, and I use table method because it's a small population. I withdraw 1, and then I will have like the probability change for my second selection dramatically. But then we talk about in page 3, it's about, well, if it's a huge population, let's say all the teenagers year 17 years old, then you withdraw 1, you take 1 out, it doesn't change the probability dramatically for the next one. It's insignificant change. So we'll treat that as a binomial distribution. So we will ignore the fact of like total reduced by 1 and the events, the targeting people reduced by 1. It's okay. So it will still be roughly the same proportion because the sample size is too large. Then therefore we say X is not binomially distributed. Before X is hypergeometric distribution. It's not binomial. It's with the without replacement. But now we assume it's a case with replacement. It's assuming, but it's a very, very close enough assuming. So that's a binomial distribution with A and P. Therefore, the expected X is N times P, and variance of X is NP times 1 minus P. Therefore, we have get back P hat. Okay, the red thing is very important. What is P hat? P hat is capital X divided by N. It's the number of X you have over the sample you have. Okay, the N is the sample, and X is like what you're interested in, the number of females or the number of males, that's the X. And also you know that X is binomially distributed. Therefore, we have all this calculation here by using the EAX plus BC and the variance AX plus BC. We find the expected of P hat will be the same as the true population mean. And then the variance of P hat is P times 1 minus P divided by N. Okay, and then standard deviation is square root of that. Okay, so that is what we know so far. And let's have a look at example 5. Okay, again, P hat equals to X over N is very important. Okay, it's very, very important. We'll use that for the next question. So suppose that 70% of 17-year-olds in Australia attend school. If a random sample of 20 is chosen from this population. Okay, so you have a 20 chosen, which N equals to 20. Okay, with N equals to 20. And we have 70% is the true population. So your P is 0.7, well, 70%. Your P is 0.7. That's the true sample proportion, or true proportion, population proportion. So it's 0.7. So let's say let X be the number. Well, can you see the method of doing this question is totally different from what you have done for the previous question. What we miss here, we don't have the total population. We don't have the total population. So for the previous question, see, I have the total population, 6 blue, 4 red, I know the total is 10. But here we're missing that, okay? We don't have that piece of information. Therefore, it must be a binomial distribution. So I'll say let X be the number of 17-year-olds Australian students attend school. Attend school. Okay, so X will be binomially distributed with 20 and 0.7. Well, that's selecting 20 people, and every single person will get a 0.7 of the chance attend school. So X is just nothing to do with the proportion yet. Okay, nothing to do with the proportion yet. It's just like X people, like 20 here, and I want to see how many actually attend school. Okay, so A is asking us, find the probability that the sample proportion is equals to the true population proportion. So I'll just say probability of P hat is actually equals to P. What is P? P is 0.7. Okay, I want P hat. I want this 20 people I select. That proportion exactly give me the true proportion, which is 0.7. So that's what I'm trying to find. Okay, what is P hat? P hat is X over N. What is N? N is 20. So you find, like, for example, 4 students. So over 20, 20 is the sample. So 4 on 20, 20%. will be the proportion, okay, sample proportion. So it's the number of x over your number of total that give you the 0.7. So therefore, that question changed to x equals to 14. Okay, that question is not a proportion question anymore. Nothing to do with the proportion. It's just a purely binomial distribution. Now what you're trying to find is probability x equals to 14. What is x? X is binomially distributed, right? X is binomially distributed. So, well, like if I know the sample is 20 and I want to achieve a particular sample mean or like a sample proportion, I just need to figure out how many students attend school I need 14. So that's just a binomial distribution with 14. And I will have like, that's a binomial distribution. So I will just open my calculator and have a look. Okay, that binomial is with 20 and 0.7. Okay, 20 and 0.7. Menu 55D, because I want a single value 14. So number of trial is 20 and successful rate is 0.7, and I want a 14 success is a PDF, not CDF. I click OK, that gives you this rate, 0.1916. How many decimals? Well, I don't know. 0.1916, just give 4 decimals. Okay, so that's what we find here. So this type of question, if it's a binomial question, the question will change into a binomial question, not a sample proportion thing. It's totally different from the method you use for the really exact way, like we do for first page and second page. So it will be different. Okay, B. The probability that the sample proportion lies within 1 standard deviation of the population proportion. Okay, within 1 standard deviation, I need to find what is the standard deviation for p hat. So, what's the variance of p hat, everyone? Well, you know expect of p hat. Let's say expect of p hat must be the same as the true population proportion, which is 0.7. What's the variance of p hat? Look at both on your page. P is 0.7 times 0.3, 1 minus P over what? 20. Okay, over 20. 0.12 divided by 20. Well, I'll leave the answer like that. So I know the standard deviation of p hat is square root of 0.12 over 20. Okay, so that's the standard deviation. Let's save this number because it's a number like you don't really want to type every time. So I will go square root divide 0.7 times 0.3 over 20. Okay, how do we save a number? Control VAR, save that as A. So control VAR A. So A is represent 1 standard deviation now. So what I need is, well, what I'm trying to find, B. The probability that your sample proportion is within 1 standard deviation. Well, whether equal, not equal, that's fine. Okay, within 1 standard deviation. Okay, what's within 1 standard deviation? Minus 1 standard deviation plus 1 standard deviation. So that is 0.7 minus A. Okay, minus 1 standard deviation. And 0.7 plus A. So it's about that. 0.597. Okay. 5975 less than p hat less than 0.825. Okay, if now I know what the proportion of p hat should be, I'll change my p hat into x over 20. Okay, p hat is x over 20. I always trying to put that into the binomial distribution back to x. Okay, I don't want to have it with population proportion p. I want x. So I will times 20 on each side. Okay, I'll times 20 on each side. So this number times 20 and that number times by 20. Well, leave exact. Okay, leave exact. Leave as much as, well, use exact, use the calculator notation to find it. So it's in between 1.95 and 16.05. Okay. 1.95 less than x less than 16.05. Can I ask you what is x? Do you know what is x? Well, what I'm talking about here. Okay, is that what possible value it can take? Can it take 1.9 or like 11.9? It must be integers. Okay, it's like number of students, number of persons, so it must be whole integers. Okay, can you tell me what integers is actually inside those range for x? Like what you can take? 12, 13, 14, 15, 16. Okay, you can't take 11. What? Well, even though that's 11.05, you still can't take 11. It must be the integers in between those two numbers. Okay, you draw that on the number line. That's 11.95. That's 16.05. What integers in between those two values? It doesn't matter round down or round up. It's just purely what you can have for x. Okay, in between those two range. So the x you can have in between that is 12 to 16. Okay, 12 to 16. So that's probability 12 to 16. I'll adjust the domain. Okay, I'll adjust the domain. So it can take 12 to 16. So x is binomially distributed, 5, 5e. I have 20 with the trial. 0.7 is my successful read. And 12 is what I want, and 16 is what I want as well, like 12 to 16, lower and upper bound. Okay, and press OK. That's 0.7796. No, well, it's better to write it out. It's better to write it out. But like, if you have the correct answer, then it's correct. It's more clear for yourself to see it as well. Well, I don't have enough space. Can you just do C for me, please? Give you 2 minutes. 2 minutes should be enough. Well, it's exactly the same as the previous one. That lies within 2 standard deviation. Well, I hope that's approximately 95% because that's not 2 standard deviation. I'm not sure because I don't know the answer. So you track that for me. Finished? Finished? Answer should be 0.9752, approximately that. Okay, and that is 302 decimal, that's fine, but also should be that. Okay, you subtract 0.7 from 2 standard deviation and add 2 standard deviation to 0.7. You have a proportion approximate 0.495 and 0.905 in between that. And you know p hat is x over 20, so times 20 on each side. X will be in between 9.9 to 18.1. But you adjust that to the whole integer numbers, that will be 10 to 18. And you put into the calculator, you have 0.9752. Any questions to that? No? Okay, next one. Let the random variable p hat represents a sample proportion observed in an experiment. If p is 1/6, what is the smallest integer value of the sample size, such that the standard deviation of the p hat is less than or equals to 1 on 216? Oh. Wait, what's wrong? It's less than that. So I want the SD of p hat is less than or equals to that. Okay, what's standard deviation of p hat? Square root of, what is the formula? Variance of p, p1 minus p over what? N. Okay, so, well, let's say the square root of p is 1/6 times 5/6 over n. Okay, 1 to 6. Let's see what's 1 to 6 divided by 6. 36. So 6 to the power of 6 to the power of 3. And then I will square both sides. You will have that. And you will have, that's 5/6 squared times the n to the other side. Well, 6 squared. Okay. They're all positive. So what you want to do is that can times 6 to the power of 2, and that will become to the power of 4 times 6 to the power of 2 on each side. Well, no, sorry. Actually, you can times 6 to the power of 6 on each side, and then just get cancelled. That's 5 times 6 to the power of 4. That's now equals to n. Okay, our standard deviation of that is less than this, and therefore I want square root 1/6 times 5/6 over n is less than or equals to that squared. So that's the variance. Variance is less than that. That's 1/6 to the power of 6. And then this side is 5/6 to the power of 2. Then I will times 6 to the power of 6 on each side. And just greater or equals to, well, what's that? 5 times 36 times 36. So 6480. So what is the smallest integer? So n minimum will be 6480. So at least needs to be 6480. Well, that's a part 1 exam type, like you just using formulas, apply for it directly, just solve for it. It's just one variables, and you're trying to solve for that. Any questions? Any questions? No? That's just using formula, okay? The expected p hat is P, true P. And the variance of P hat is P times 1 minus P over N. Okay, question 7. Suppose that 80% of all 16 years old play basketball. Okay, 80%. If a sample of size 4 is taken, find the probability that the sample proportion lies within and including one standard deviation of the population proportion. Okay, so what I have is, first I will set let X be the number of 16-year-olds play basketball. X is binomially distributed with 4,0.8. Okay, 4,0.8. And then the expected P hat must be 0.8. The variance of P hat, it is 0.8 times 0.2 over 4. Okay, that's 0.16 over 4. That's 0.04. Then SD of P hat, that's part 1 exam, of 0.04, that's 0.2. Okay, that's 0.2. Alright, find the probability that the sample proportion lies within and including one standard deviation. So that's the probability of 0.8 minus 0.2, smaller or equals to P hat, smaller or equals to 0.8 plus 0.2. That's within one standard deviation. Okay, 0.8 go up by 1 standard, 0.1. So probability 0.6 less than or equals to X over 4, because there's 4. That's 1. So that's probability of 2.4 X and 4. What's in between? 3 and 4. That's probability X equals to 3 plus the probability X equals to 4. Okay, only 3 and 4. Well, you can say 3 to 4. It's alright as well. So I'll set menu 5. Well, I'll use E. Number of trials is 4. Successful rate is 0.8. Lower bound is 3 and upper bound is 4. 0.8192. 8192. Okay, 0.8192. Okay, same as the first example I showed you today. Any questions? That's the second stage of the question. Okay, that's first stage is the first 2 pages is talking about the really exact hypergeometry distribution of the sample proportion. The second one is like, because the population is too large, I can't figure it out. And withdraw, like take one out, it doesn't really affect that significantly. So I will just treat it as a binomial distribution. That's the second type. Okay. And the third type, well, we have the third type now. The third type is very interesting. That's like really approximating. Okay, it's really approximating. A is really accurate. B is quite accurate. And C is like roughly accurate. Okay, so it's the normal approximation. Do you remember we do the last chapter? I rushed through last Friday of the last exercise. When the binomial distribution get too large, the number is like NP greater than 5 and N1 minus P is greater than 5, then we treat, say, N is large enough, and then we can use a normal distribution to do the work. We treat that as a normal distribution, okay? And it's not very accurate. It's like about 5% difference. Well, like they say it's approximation, then I'm not accepting it as it's not, but like if they ask you to do that, you will do that. So nothing difficult. You just change binomial to normal and use the same mean and same standard deviation and do whatever they ask you to do. So here is pretty much the same. So when the sample size n is large, then the sample proportion has approximately normal distribution. So previous one, I'm talking about x. Can you see the difference? I'm talking about the x. I'm not talking about p at all. I use the p, change it back to x, and then I find use binomial distribution to find the sample proportion, like the required one. But now I'm backing to p now, p hat now. So I will say, you know that expected p hat is p. Because like say x is binomially distributed with n comma p, and p hat equals to x over n, and therefore expected p hat must be p, and the variance of p hat is p1 minus p over n. That's what we have, and standard deviation is the square root of that. But we use x distribution to work on probabilities. But now I'm not jumping back to x. I'll just use p hat. I will say when p is large enough, how large? I don't know. Maybe times together give you 5 again. Well, the question will tell you whether you should use approximation or not. Like if they doesn't say which one you need to use, you use binomial. Unless it says use normal approximation, then you use normal. Same as the previous topic. So now your p hat is like, I would say, approximate is a normal. Well, you don't need to write that. Okay, you will say p hat is normally distributed with p, and standard deviation is that. Well, I should write variance here, so I'll write variance inside. So if p hat become a normal distribution, okay, p hat become a normal distribution when p is large enough. Well, when it's large enough, question says large enough, then it's large enough. And you just do whatever the question asks you. So when they say it's a normal approximation, they use the same mean and same standard deviation as the binomial. And then you treat as a normal distribution. Okay, let's just show one example here. Assume that 60% of the people have a driver license. Find the exact probability that in a random select sample size of 200, okay, 200 is very large. Think about before we just select 4. Select 10, select 20, now it's like 200, okay, it's quite large. And more than 65 of the people have a driver license. Okay, find a exact probability, can you see that? Find the exact probability that in a random select sample size of 200, more than 65% of people have a driver license. So that needs to be binomial. If it's exact, I need to go binomial. So I'll say let x be the number of people with driver license. So x will be binomially distributed with 200 because you select 200, and the true rate will be 0.6, not 0.65. Okay, the true rate, that's the true population proportion, which is 0.6. And you know p hat is x over 200. For A, what you need is the probability that the p hat is more than 0.65. And that is the probability that the x over 200 is greater than 0.65. And that is the probability x is greater than, well, move 2 decimals, 130. X is greater than 130. But it must be in between 130 and 200. Okay, in between, well, actually it's 131 to 200. It's greater than 130. I want greater than 65%. I can't take the 130. So this probability is actually 131 to 200. I just have 200 people. So that is the correct range if you type in the calculator. Menu 55E. Okay, I have 200. I have 0.6, not 0.65, okay, 0.6, and 131, and 200. Okay, 0.0639. Okay. 0.0639. This is the exact. Okay, this is the exact. Why is exact? Because I'm talking about the X. How many people need to have a driver license in the sample? When it equals to 130, there will be exactly 65%. But I need to greater than that, larger than that, more than that. So I need to start from 131. Okay, 131. Okay. What's the expected p hat, everyone? 0.6. What's the variance of p hat? Give me an equation, it's fine. 0.6 times 0.4 over 200. 0.012, okay. So now I want B, using the normal approximation, find the approximate probability that a random select sample of size 200 is more than 65% of people with a driver license. Now it's approximate, so p hat is approximately normally distributed with 0.6, 0.012. That's the variance. Okay, I'm not writing the square roots, the square form. So 0.1012 is the variance. What I need is the probability of p hat greater than 0.65. Okay, p hat greater than 0.65. And I will have the calculator. Menu 552. Okay, 0.65 is the minimum. Infinity is the maximum. The mu is 0.6 and the standard deviation is square root 0.012. 0.012. Wait. What? Just copy. Yeah, 0.0012. Okay, square root of that because you need standard deviation. Well, I need to change that a little bit. That's 0.012. That's 0.012, and that is approximately 0.0745. Well, it's about 0.1 difference. Okay, it's about 0.1 difference, 0.01%, 1% difference. It's still quite huge. Okay, it's still quite huge, 1% difference. Well, it's better than last time. Okay, it's better than last time, 5%. So it's alright to use this method, but like unless the question asks you, do not do that. Okay, you use exact. Exact is that, but now you have that as approximation. Just how you use normal approximation. Okay, next one. The proportion of the voters in the population who favor candidate A is 52%. Of a random sample of 400 voters, 230 indicate that they would vote for candidate A at the next election. What is the value of the sample proportion p hat? Okay, what's the sample proportion? Can you see that's a lowercase p hat? It's not a random variable. It's just like what this time. Okay, at this time, what's your p hat? Okay, so A is very easily calculated. P hat, lowercase p hat, is just 230 over 400. Okay, you just want to know the sample proportion. 400 is your sample. Okay, 230 over 400. 0.575. That's the lowercase p hat. I will make it like really looks like a lowercase p hat. Okay, B. What is your true P? Like the true population proportion? 0.52. Okay, don't forget your true P is 0.52. It's not 0.575, even though that's one observed. You observe that is the sample proportion. It's not the true proportion. So when you calculate expect P hat, what's the expect P hat will be? 52. And what's the variance of P hat? 0.52 times 0.48 over what? 400. Okay, that's the 400 sample. Okay, 400 voters. So that's the 400. 0.52 times 0.48 divided by 400. 0.000624. Okay, 0.30624. Okay, that's the variance. That's the variance. Okay, B says find approximate probability. Okay, approximate probability. They treat the second one as exact. Okay, the X binomial is the exact, and this one is the approximation. Binomial is the normal is the approximation. So find the approximation that 400 voters who favors in candidate A is greater or equals to P hat observed in this particular sample. So capital P hat is approximately normally distributed with 0.52, 0.00624. And I want to find the probability P hat, which is greater or equals to the true sample, the observed one. The observed one is 0.575. And then the rest is the cast. Because it's normally distributed, 552, 0.575 to infinity with mu 0.52 and standard deviation square root of 0.000624. Okay, so that's the population, well, whether it's greater or not, it doesn't matter because it's a normal distribution. It's continuous random variable, so it will be the same. Observed one, we have 0.01384. 0.01384. Well, like, you can find the exact, okay? You can find the exact. How do you find the exact? The exact will be P hat greater or equals to 0. Well, that's probability of X over 400 greater or equals to 0.575. And then you find probability X is greater or equals to 0.575 times 400. That's 230. Well, you know that already. So greater or equals to that. And then that's a binomial distribution. Menu 55E. So 400 with successful rate is 0.52. And the lower bound is 230. And the upper bound is 400. And that's 0.01555. Okay, can you see the difference is about 0.2% difference. It's quite good. Okay, this time is quite good. 400 is better than the 200. Can you see the larger the n, the more close to the true value. Okay, that's about 0.2% difference. It's better than last time 1% difference. That's the exact. Okay, that's the exact. That's the approximate. Okay, I'll save that first.